Hello everybody and welcome to another Würth Elektronik eiSos webinar. My name is Thorolf Schwan and I'm going to moderate this webinar today. So we are very pleased that you took the time to participate in our webinar today. So the topic of today's webinar is Automotive Requirements to Passive Components AEC-Q200. Our speaker today is Loran Völkl, who is working as Global Business Consultant for WE ASP. He will hold today's webinar and is going to answer all your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. So this means that you cannot ask us questions via microphone during the webinar, but nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. And you'll find the chat function in the webinar control panel. Today's webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are around about 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just send us an email at eisos-webinar@we-online.com. We will try to answer all your questions as promptly as possible. So at the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you'll find the time to fill out the survey and help us to improve our webinars. You will receive the link to the presentation as well as to the recording of the webinar within the next few weeks. So now I will hand over to our speaker Loran, and I wish all of you an exciting webinar.
Hello, everybody. My name is Loran Völkl. I'm application engineer, field application engineer at Würth Elektronik, and I'm working with Würth the last 20 years. Today, I will present something about automotive requirements and components, because sometimes it's very important to make a big difference between industrial components and automotive components. Why, you will ask, why automotive components? What is that so important? What is so different from standard? Well, first of all, they have different requirements. They have different quality levels and also different process flow charts, and they are offering different PPAP, IMDS, IATF, AEC-Q200. But what means all these short letters together? So I will try to go through this short explanation. And first of all, we start with WE ASP, which is nothing else than Würth Elektronik automotive standard products. And if you talk about TS 6949, or since 2017, it calls International Automotive Task Force 16949. Mostly OEMs already using that kind of certification. That's which is described the facility, the whole production, and you're certified to be IATF 6949. If you talk about IMDS, International Material Data System, this is a database where all the supplier can put what kind of really material contain their products. So Würth Elektronik was one of the, I say, quite in the beginning of this IMDS database, and we put all the information which contains our product, and also the supplier who's supplying this information. AEC-Q200, this is the Automotive Electronic Council. The 200 means for passive components. If it's 100 is for active components. We belong to the 200 because we have these passive components, and they define the different tests and what you have to fulfill if you want to be sure that the quality level is automotive requested, so automotive standard. The PPAP production part approval process, it means that you will have something like a warrant and release for the components that the supplier guarantee for you, like a customer, with different level, of course, and contain much more details of the component. If you talk about PPAP, PPAP are 5 different levels. So everybody uses this standardized parts approval process, the 4th edition, and this is, I guess, well known in automotive industry. That is something which it's give you a feeling about the quality of the components, and also not just to give you a feeling. You are the test reports, you have different certifying that this process have been done. Würth Elektronik offer excuse me, 2 PPAP levels, PPAP level 1 and 3. These 2 levels are different because the PPAP level 1, it means only just the part submission warrant, PSW, part submission warrant, and the data sheet, and then you have documentation for the rows reached documents, which means that not hazardous components have been used. And the PPAP level 3, it's a much deeper and contain much more documentation, not only just the test result and the process flow charts. You have also a control plan, the failure studies, what kind of performance have this material, and much deeper knowledge about the component what you have been used. This is a PSW document, like looks if when you are buying a component with a PPAP level 3. Very important that the supplier and the customer both are signing this document, that this is kind of contract. So the supplier guarantee for this different tests have been done, and also the customer, like you, when you use this component, please always, it's a must to sign this document and send it back to us, because only then it's the really, I would say, contract between these 2 companies that you will use the component like defined, and we guarantee in this definition that the component will withstand all these different criteria. In PPAP level 3 additional, we are making that if we test one product, we make a product family test. It means if you buy a component in PPAP level 3, and this is an inductor, like here, example, a PDA, and you use an inductor with 4.7 microhenry, and you find out, oh my God, this 4.7 microhenry for my DC-DC converter is not so suitable because my ripple output current is too high. I need a higher inductance to reduce the ripple, and you change to 10 microhenry. You don't need to re-qualify, or you don't need to ask for all the documentation, because we have this documentation for the same size, the same product family, which is contain all the values available from us. So this is an advantage, that you can get all these different value with one single certification, and you have all this because we are testing not only one value, we test all of them. When we make a PPAP level 3 for one component, we make not only for one value, we test them all. What kind of tests we make? This is again the same example on the PDA. You can see here that we are testing the high temperature exposure, the temperature cycling. We make also resistance to solvent, mechanical shock, vibration, 3D axis. ESD test make no big sense, but it's requirement of AEC-Q200. Maybe some components, they are ESD sensitive. Inductor doesn't matter, but we still make them. Soldability, this is also very important. Even it is not in the documentation here, we make even 5-time refill test process. So we are very I would say careful that our component must be withstand all these 5-time reflow process as well. So this is just an example of one component. by the IMDS, this database. If I remember, it was more like 15 years ago. It was starting from the Japanese car industry, and some German car manufacturer is also following after that. Actually, it is described what's contained, in fact, is what kind of material are containing. If you look in this IMDS database, you will see Würth Elektronik have a lot of different components already listed here. And if you choose again this PDA from us, you can see something like, I was really impressed about this information. The wire, the copper wire containing like 0.35% phosphor. I was like, what? Copper, it's containing phosphor inside? Yes, this is chemical, which I did not maybe pay attention in my study, and it is like normal to have that. But you can see, you can on atomic level, everything what we are using inside, and you have no problem to see also which is the supply of the wire or of the glue or so on. IATF 6949, this is a new certification. I guess the most automotive already are recertified for IATF 6949. This is the next international certification since 2017. And yeah, AEC-Q200, it is the Automotive Electronic Council for passive components. It's the 200 is for passive components. You have also some appendix like 006. This is for measurement method for fuses, which is not Würth Elektronik component, but you can see here you get all these different tests with a qualification sample that we have done, and you can be 100% sure they are tested and they are withstand the parameters. For the temperature grades, there are different temperature grades. We offer 4 different grades from 0 to 3. Grade 0 means in temperature grade 150 degrees Celsius operating temperature, and grade 3 it is 85 degrees Celsius, which is quite very usual. The grade 1 is also the most used one, and we have a grade 2 which is 105. These have been used for the snap-on ferrites because the snap-on ferrites, the ferrite core himself is not the problem. There's more like 150 degree. The problem is the enclosure, this plastic housing. It's maximum 105 degrees Celsius operating temperature. 85 will be not so good because it's too less. 125 is too much because it's plastic. Guarantee is 105 degrees Celsius. So there are the different grades for that. For the temperature definition, if we talk about temperature, it's very important to realize that if you read in the data sheet that the operating temperature, it is from minus 55 to plus 150 degrees Celsius, then you have to be aware about the self-heating of the component. In this example, you can see this inductance of 1 microhenry. If you apply a current of 22.5 amp, the component will generate a self-heating of delta T 50 Kelvin. It means if you apply 22.5 amp through these components, because of this resistance and of this big current, you may have a 50 degree above the ambient temperature. So you have to add on always this self-heating to the ambient temperature. If the component is qualified for operating temperature 150 degrees Celsius, it means if you apply the maximum current, your ambient temperature, it is restricted to be maximum 100 degree. Because you have 100 degree ambient and no DC current, already the component is 100 degree, and then you put the maximum current, which is generate 50 degrees Celsius add on, you have 150 degrees Celsius on the component. If you have an ambient like 125 degrees Celsius, and you still want to use these components, it's possible, but not with the maximum current. You have to derate that. You need to look in this derating curve, and I will say at 125 degrees Celsius, you can admit not 22.5, you can admit maximum 10, 11 amp. That's the absolute limit. If you exceed these 10 to 11 amps, you may overheat the component and that can be destroyed, or you run out of specs and is no more warranty for right function. So be aware always about the self-seating component and what is your ambient, and calculate that ambient plus the self-seating should not ever exceed the maximum operating temperature. Which kind of automotive standard products in the portfolio? There are a lot of different axial toroidal cores which you can put to the wires. We have some nice chip bit ferrites. We have through hole technology inductor, surface mount technology inductance. Brand new are these nanocrystalline cores, and also this manganese zinc cores, and also very new are this steel spacer. This is the SMT spacer, which you can pick and place with a machine, and yeah, you can put for the grounding, you can put for fixing for the PCB, and also this soldered contact finger in automotive is quite new or special. In a new catalog, you will see them. For storage inductors, we have also two new products. One is the PD. It's similar to PDA, just different base. I will show you what is the big difference. And my favorite is MAIA. I like this MAIA because it's a very, very temperature stable and excellent good shielded storage inductor. And I will show you that later. And new products are RF inductors as well. It's a multilayer ceramic inductor, something like if you make radar or keyless entry or something like that, you will need some high frequency ceramic inductor. And now we have also AEC-Q200 automotive standard products. You may ask why we use so many different core materials for our ferrite cores. Well, we could use the best one. This is the nanocrystalline cores. It calls AENA. It has the most bandwidth, excellent permeability. There are one problem. They are the most expensive, of course. Nanocrystalline cores was in the past made from two different manufacturers only because of the license, and now the patent is due and everybody can build them. We have now also investment for making nanocrystalline core, but it's a technology. It's quite expensive, and not always you need to drive a Maybach. Sometimes it's also good to C-class. And because of that, we have nickel zinc cores, which is very simple. Also, I would say much more simple to produce because it's a powder sintered. A manganese zinc core, a little bit more expensive, or it was too expensive in some cases, like nickel zinc in comparison. And then we introduced this magnesium zinc. This is between nickel zinc and manganese zinc, and also from impedance in the low frequency. It's not that much good like manganese zinc, but not that much expensive like manganese zinc. So it's something between, and it's a quite good material which is getting more popular and popular. If you use a nickel zinc core by using on the wiring, if you have radiated emission or you have immunity problem for your black box, you can put that on the wire, and sometimes it's very, very reliable and excellent usage for without changing anything on the board. It can go up to 150 degrees Celsius operating temperature. Doesn't need to be coated because the surface himself is like an isolator. It's no problem at all. If you look to the magnesium zinc, the magnesium zinc in comparison with nickel zinc has in the lower frequency a much better impedance. So you don't need to put 10 turns on nickel zinc to reach the same impedances by magnesium zinc. Maybe you can reach by 5 turns. It has much better AL value as well, and it can goes very, very high in the lower frequency for the impedances. Magnesium zinc is also not coated like nickel zinc. Manganese zinc is already coated. Why? Because the manganese zinc surface is already conductive. It may generate short circuit, and that's the reason why we coat them. It can be up to 150 degree, the magnesium zinc 140 degree, but this is very good for a low frequency, especially if you have around 1 megahertz or maximum 10 megahertz, and in the low kilohertz frequencies, it's also operating quite with a good insertion loss and can be used for cables, or if you want to shield somewhere antenna or something. The nanocrystalline cores, they are the I would say, the most efficient one because of a very high permeability. You can reach by one turn already much better, like 10 turns nickel zinc. And advantage is also a very temperature stable because it's a not sintered material. It has one problem, well, not problem, I would say, one disadvantage. It's very pressure sensitive, and it can break easy. That's the reason why we don't coat them. We pack them into the plastic housing. So if you look for the nanocrystalline core, you will get them always in a plastic housing. It's a very stable plastic housing, which is give you a mechanical stability and also not a problem of cracking or something, and the operating temperature is under 125 degree, mostly because of the plastic housing and not because of the material himself. Core losses. What is core losses? What makes in this ferrite, how it works, the ferrite core, if you put under the wire? First of all, you have this energy, which is it could be a bad energy like EMI noise. But what happened with this energy? What into the ferrite? Well, many people say it is absorbing, which is not so correctly, because in the physics we have one law that I would say the first law in physics is energy never get lost; it always transfer in another form. In fact, ferrite core transfer these two vectors of energy like H field and electric field. This making the ferrite through the eddy current losses, core magnetization, demagnetization, make that the core transfer this energy into heat. But believe me, even if you use a very nice thermal camera from Fluke, you will not see the ferrite getting hot if you have not if you have an EMI problem. The only one thing that I can imagine that you can make the ferrite to get hot if you have this immunity test at 400 volts per meter, and you have a really quite crazy long wire, and you have exactly the resonant point reached with the ferrite, you can make by 400 volts per meter the ferrite running hot. If you ever make EMI noise that the ferrite start to get hot or turns into red, you don't have EMI problem. Believe me, you have a safety problem. Run away fast you can, because you don't talk anymore about 400 volts per meter. And if you generate such noise, it's not good for your health. Normally the ferrites doesn't get hot, and like I told you, only by immunity test it could generate sometimes to getting a little bit more hot. On the PCB, you can do a lot of things using a chip bit ferrite. A CBA is a chip bit ferrite automotive, can go up to 8 amp size from 0402 to 1812 size. It's a very good solution and cheap solution to place them on every VCC, on every IC, that you can block the noise which is generated from the IC to not interfere with another device or modules. We sort them in 3 different category. When I was product manager for ferrite beads, I say we have some ferrite which are working in very high frequency, and in a low frequency they are not so, I would say, not efficient. So I define them to be their high speed one. So I tell all the ferrite beads which has below 50 megahertz, not so extraordinarily good impedance, I say they're high speed because they are getting in a very high frequency good impedances. And the wideband ferrite, my idea was to put all the ferrite bits in wideband, which you have a large bandwidth of filtering. You can have them from 1 megahertz up to several hundreds megahertz, a very wide band, a very nice coverage of the frequency. Not good for high-speed signal because it will be filtered as well. That's the reason why if you have a 10 megahertz high-speed signal, use the high-speed one, which is a 10 megahertz, is not so effective. But the wideband definitely, if you have large values, large frequency range where you have to cover. High current, I define them everything what was at least 1 amp. All the ferrite bits which has a current minimum 1 amp, I say they must be high current one, and they can go up to 8 amp. And by high current, you don't have high speed, or mostly we try to have them wideband. Of course, you have them some which are working in a very high frequency as well. From strategies, just because of the withstand of 1 amp, So the thickness of the silver layer is a little bit thicker. That's the one thing which make them high current version. This is a CT scan on a chip bit ferrites. You can see the internal layer. This small internal layer looks like stairs. You run on the stairs. This is the internal layer. It's a pure silver. This is pure silver because even it's expensive, but it's the best conductive what you can do in this process. And you can see on the left and right, this is this the zinc electrode with a nickel layer barrier for whisker to avoid whisker. So this is on the standard chip bit ferrites. If you have problem by inrush current, load dump test, something like that, if you, then I would suggest not use the standard chip bit ferrites, because by standard chip bit ferrites is not recommended to exceed the maximum current. Even if you say it is just few milliseconds. Few milliseconds, it can be too much for them and it may be damaged. Even you test them and you don't see any damage, believe me, you don't see it. But in time, it will be damaged. You don't know. It will run 30 hours, 30 days. If it's 30 years, no problem. Nobody cares. But sometimes it can happen that it's running only just 30 days, and it's nothing more worse than when you release a car. I will have to think so to be careful because of NDA. When you release a car and running on the street, and after 30 days it's stop it because the wrong chip bit ferrites have been designed. For this inrush current, I would recommend, if you know that you put your current clamp from your scope and you see that the input capacity every time when you start it have a inrush current, you will need the MPSA. This is a different manufacturing process. It has a much lower this resistance. We can go very down to 4 million this resistance. The current, the nominal rated current is still can be 8 or 10 amp, even a little bit higher because of the low this resistance. But this one will withstand pulses. It is made in that way that you have for a very short time, micron milliseconds, you can overshoot them the nominal current. And if you go to our website and you discover this Red Expert software, you can in Red Expert software see if you go to the MPSA or the MPSB as well. The MPSB is more for industrial, MPSA for automotive. You can see how long, if you measure the pulse and you know you have for short time 20 amp pulse for 2 milliseconds, how many times this component will withstand this pulse. If you see that this pulse is only once, then I would say this is not a ferrite bit, it's a fuse. If you see only 50 pulses, then you can decide by yourself, do you want to sell to the customer a device which he can use it for 50 times, and then he buy another one from you? It's also a good strategy. Or you choose a ferrite bit which withstand at least more like 100,000 pulses. And then you can sleep well at night and you don't have to carry that this component will be damaged. So I would recommend to use components which is more pulses than 100,000 it's withstand, and you can see on the window how long is the pulse, how high is the pulse. If you don't find anything, okay, forget multilayer, put a wire wound inductor, because the wire wound doesn't have this problem by inrush. Of course, if you use a very thin wire, it could burn as well. You know, I think every electronic component somehow inside must work with smoke. You know why? Because when the smoke escapes, it doesn't work anymore. So it's same by the automotive components. The most used standard components are these rod core inductance with through-hole technology. This is very cheap. It can be withstand large currents. If you have an electric seat, a good electronic seat, if you open that and you look on the motors, you will find on every motor 2 of those. I found last time in one seat 62 small rod core inductance. Crazy, right? Only one seat. Yeah, that could happen, but it's cheap and it's very functional. If you want to place them a little bit better and more process optimizing, you can have them like SMD as well. For SMD technology, you can use this pick and place machine with this small cap on the top. Of course, if you choose the 45 amp one, which is quite solid and big, you will need something, not a vacuum pins, that it will not work. You need something which is grabbing the component himself. This is an example from a customer who was not passing the EMC test using a small DC-DC converter for motor. It was quite simple design. You go to EMC lab. He failed the EMC conductor emission test and asked us what we can do here to improve his design. We saw it. He used two inductors in form from rod core, which is cheap and easy, but rod core doesn't have a shielding. So we say, how about to use, instead of rod core inductance, put some shielded inductance, and because of the surface of the second layer, so we was only two layers on the top layer, it was a lot of empty space. We say, come on, float this empty space with ground and make nice vias to the bottom ground, and keep finger crossed and remeasure it. The customer tell us, and I remember he, because I was talking to him, and he say he go back to the EMC lab, and the EMC guy, when he saw his version 1 and version 2, he say, hey guy, on the schematic I don't see any change. What you did change here? And he say, yeah, I changed the inductor and I changed the PCB a little bit, and looked into the PCB, and the EMC guy asked him, do you think that you will pass the EMC test now because your PCB is green instead of yellow? He was a little bit, not so motivated to make any measurement, but the customer asked him, hey guy, I'm here, I'm paying for your measurement, made that. Finally, he made the measurement, and he said it was so funny to see the EMC guy. He started to be nervous. Because of, you can see here the noise floor of his machinery. That's the noise floor, and this is what is the device noise making. So from here to here, only by changing the inductor and float a little bit the ground, I'm honest to you, this is a lucky punch. Not every day is a Sunday. It's not so easy to do that all the days, but sometimes it's so satisfaction when when you can make the EMC guy to be nervous because he doesn't believe that this is possible. And it's nice to have that. I really wish to you to have at least one experience like that when the EMC guys start to be nervous, because when you are so close to the noise floor, you will see they will start to recalibrate, to check if the thing is open. I had once the experience with one guy who has extremely low noise by emission. The EMC guy even opened the door from the anechoic chamber to see if the receiver is working. This is a good EMC design. Then, what you can do by this different cores, of course, if you look this drum core like a PD2, and you make a magnetic cut in the middle, you can see the magnetic field is breaking out from the middle. You can see the highest magnetic field is close to the wire, of course, and this is indirect dependent of the distance. If you put around this drum core a shielding ring, like the shielded inductors, like the PDA, you can see the magnetic field is turning back on the shortest way to the core. You have a small gap on the top and the bottom, so that's the reason why I not recommend to route anything under the inductance, but it's still excellent for EMI. And please use for storage inductance in your DC-DC converter always a shielded one. It will be paid back later in the EMC chamber. This is a nice experiment made for my colleagues in the EMC lab. They took a 10 microhenry inductor in a DC-DC converter. The switching frequency was 2 megahertz and 1 amp output. Not even track the EMC low requirement. Just make a record of the peaks and take a soldering iron, desolder the unshielded inductor, take a 10 microhenry shielded inductor instead, and solder back to the PCB. Try to not change anything on the setup. No touching wire or position or something, just changing the inductor and remeasure the EMI. 90 dBm better. Only because change from unshielded to shielded version. This unshielded one contaminate the system. In the anechoic chamber, because this is conductor emission, in the anechoic chamber, I think the picture speaks by himself. If you use the unshielded version, and you pack them in a nice Faraday cage, okay, it's good. But if not, I recommend to use this little bit, maybe a few cent more expensive shielded version, and you will be happy in the EMC chamber. The PDA, this is the most popular inductor, withstanding a lot of temperature and other shocks and everything, have a nice plastic base with an excellent coplanarity. It's a very good, well-known components with different size. And if you compare that with the new PD series, both look same, both have same inductance, same characteristic, maybe DC resistance a little bit different, but the big difference is the base. By PDA, we use a plastic base, and by PD series, we use a metal base. By using the plastic base, it's an advantage that we can weld the wire to this plastic base. You can see here the magnetic simulation of this core, and this is a cut, a mechanical cut into the um, core himself. And now you can see the big difference on PD and PDA. The PDA are using, instead of soldering junction or welding, the wire, the copper wire is welded to the electrode, which is giving an excellent coplanarity and the perfect soldering junction. By the PD, we use solder. It has advantage using the solder that we can use even multiple wires, so twin or triple wire. By the welding is possible only by using one round wire. If we want to have better this resistance, you can use bifilar wire or trifilar wire, and that's the advantage by using the soldering instead of welding. Advantage, disadvantage, always it's a matter, but many customers are releasing both. It depends on the application. Not always you need to be welded or soldered. Now you can see by the PD series, we can go up to 2.2 millihenry. By PDA, only 1 millihenry. This resistance can be even be lower because of this multiple wire. Instead of the soldering pad is same, the everything is same. Like I told you, you can have both in your BOM. It depends which is more favorable for your application. It's not a big difference. The PD2A, it is a drum core with a wire wound, no plastic socket, no metal socket, is a metallization directly on the core. That's the reason why in the manufacturing is process is very more simple, like the PDA or PD series, but is unshielded. This is well used because it's cheap for filtering, perfect for storage. If it's more like 500 milliamp output, be careful, it could be a problem. You have to pack it in a metal box, then it's no problem with no holes on that. But best is no holes. And if you have the luck and use the 7850 size, so this is 7.8 millimeter by 7.8 in a height of 5 millimeter, and you had an EMI problem, we can help you giving you the PD2SA, because the PD2SA, it's the same pad like the unshielded version, just we put to the drum core a shielding ring additional. I'm very sorry that we have only this size right now, but this is a shielded version, and if you use the unshielded version and you find out, ouch, we have a problem on the EMI chamber, maybe you have the luck that you will have the same value in the shielded version and you don't need to redesign your box. If you make a nice pad, a smart pad, which you can put PD2 and you can put also the PDA series, it's much more clever as well, but it depends how you make your junction pad on the PCB. You can see here the PD2SA has the same drum core like the PD2 without the shielding, and we add additional this shielding to that you have better magnetic field coupling and no big magnetic stray field which is going out of the core. The MAIA one, why I like this MAIA so much? First of all, when we manufacture MAIA, we took a piece of wire, we wound in air a coil, it's an air coil, and then with a fixture we put iron powder alloy and we press them together in one piece. So it's a not sintered material, it's an iron powder material. Because it's not sintered, it's very temperature stable. Ferrites are physically not so temperature stable. They have a drift by the minus temperature and plus temperature. As much higher you go, the AL value is going, the permeability is going up. If you go to minus, it's going dropping down. It's existing a high temperature series for 150 degrees Celsius, and this is really very reliable. You cannot reach very high inductance level because of the iron powder core, but for high-speed DC-DC converter, so I would say DC-DC converter, which is switching more like 250 kilohertz up to megahertz, is very, very usable and excellent, stable, and very, very good because the whole magnetic field is inside of the core. You don't have an air gap. Don't think about that it will saturate too fast because you have a distributed air gap into the metal powder himself, and that's the reason why he has a very nice, clever linear saturation and not a fast saturation like the ferrite cores. This is how it's made. When we manufacture that, we don't have a plastic socket or metal base. It's a very nice junction here on the bottom. It even don't need to be welded. So it's perfect for automotive because it's very robust. And you can see here, it's no air gap at all, no radiation. And try it. Please ask my colleague in the sales field area and ask them for samples and test it. The CHSA actually is a rod core inductor, even doesn't look like a rod core. It has a flat wire on the rod core inductor and has additional a shielding box. So you have a completely shielding box above the rod core. Maybe I can show you this picture. You can see here inside the rod core, you can see the flat core, which is welded again to the plastic socket. And because rod core make a large EMI emission, we put a shielding ring, and it's very good because going up to very, very high temperature, and also it is a good component for reliable SMD pick and place. You can see here this glue. This glue is not delivered with the component. This is just to fix during this, making this cut in this component to see how it is inside looking. So this is just fixing glue for the picture. HCFA, this is a high current ferrite core for extremely large currents. It go up to 14.7 amps in nominal or saturation 81 amp. Extremely low DC resistance, 0.6 milliohms. So we talk about microohms already. It has 3 points of soldering. The third point is just for fixing. It doesn't need to be connected to ground. And I have been asked many times, do I need to connect that to ground, or what is the function of this? This is just for fixing, just mechanical fixing, because I have the input and output on the same side. It's a flat copper wire. Flat copper wire much better like round wire because you have more surface, and a certain frequency more like 200 kilohertz. You need a surface because the current doesn't flow inside of the copper wire. It has this skin effect on the surface, and you need more surface to have a very extremely low DC resistance and also AC resistance. It's good for very high current application. It's also a shielded version. Even you can see the wire, it is shielded because the magnetic field is inside of the core. The HCIT, it is the rod core inductance through hole technology with shielding. So we took the rod core, this time not in horizontal, we put in vertical, and we put two pieces of magnetic core in manganesic zinc, and then you have a closure that the magnetic field is inside. It's through hole. You can go up to 28 amp, extremely low DC resistance. The values of the inductance doesn't go very high, but it's a small and excellent component for large currents. The MCI ceramic inductor, this is for keyless entry, like I told you. If you have some infotainment, if you make Wi-Fi system in your car, or you make any other RF, you will need some inductance with extremely high resonant points, and inductive tolerance 0.3 nanohenry. This is a standard product, also available from stock like all others. The spacer are not an EMI product, but it could be helpful for EMI if you make a good ground connection, and you don't need to use that by hand manufacturing, because this is a SMT component and you have pick and place. You can get them from tape or for tray, and you can make pick and place directly in the process. It's make your process more reliable and more simple. And you can have them even with the M3 size. We have one which have also M3 inside winding, and you can use a screw for that instead of plastic or something, and you make hand manufacturing. The contact fingers is also something new. It's a copper beryllium gold plated contact finger. You can make the grounding connection. You can make also pick and place by SMT, because it's also in the packaging from SMT machines. It's perfect to make a good current connection. I know one customer, he has stacked PCB, and instead of using a connector, he decided to use this finger contact, and he assembled that to each other, and during the assembling you make the contact with extremely low impedance and extremely good even for antenna connection. One customer I know, he's using even for RF antenna connection. It works quite very good. If you want to design something, ask my colleagues in sales for these design kits. It's better to ask always for design kit, like for one single piece, because when you check for one product family, a design kit, you have all the different values, and then you have more possibility to try and test them. If you have a own EMC lab, you can even ask for this EMC rack. This is a very nice looking rack which you can have in an EMC lab, and you have different boxes, depends on your application what you need. You can put different sample boxes there. Always when you make a measurement, it's good to have samples with you and to have a possibility to improve by on the EMC tab when you have. Other thing what I can recommend, ask my colleagues or order these books. There are different books which is like most important is magnetic Trilogy of Magnetics in the LT Spice book. In LT Spice you will find the most our components are listed. If you don't find on LT Spice when you download it, if you go to our website to the toolbox and you click to simulation software, you will find the library LT Spice. If you download and unzip this folder into the LT Spice file, you have all the components which we that measure it, and you have a model with all these parasitics as well. So we always measure the components with parasitics. You get for the parasitics free of charge delivered, so you cannot get only just the ideal inductance. The resistors and the parasitic capacity is free of charge, so don't worry about that. But really, the models in LT Spice from Würth Elektronik always measured with a network analyzer, and it's a real model. It's not a ideal model from maybe existing inductance in the universe, but not on this earth. You have always parasitics on inductance. You have this winding parasitics, you have the impedance, you have the losses. All that is included in our Spice models. If you're working and developing in Europe, but you're plant manufacturing somewhere, another part of the earth, doesn't matter. We have everything which is red covered with direct sales. All my colleagues are helping to you. Even I like this picture because even in Greenland you have somebody who can deliver. Of course, this is a joke, but Greenland. It is because of Denmark, and we have Denmark sales guys, and yeah, the country is covered for sure. I don't know any plant of manufacturing in Greenland, but anyhow, all the others is really covered from sales guys. If you want to be in touch with me, I have also a LinkedIn account and Twitter account. And if you go to our YouTube channel, you will find some nice videos where I'm measuring inductance and explain what is saturation current, what is nominal current, how is the setup for different um, um, measurement of the impedances and cores. And look on the YouTube channel, you will find maybe something. There are several videos from me in the lab made. Now I will ask if you have any question, please put that in your chat, and I will try to open now this window and try to see if any question get in and try to answer that. So I see already a few questions. Let me just make this picture bigger to be able to read it. So one of the customer asked, will be the red cube power element become AEC-Q in the future? Okay, where is my glass ball? I will ask the glass ball. I don't know. I am not the godfather of power elements, and I cannot tell you if that will be in the future or no. I have the answer, maybe. I know that all our product manager are working very hard to have all the components what we are producing to have an AEC-Q200, but pay attention, not everything what AEC-Q200 tested, it is automatically good for automotive. You will find also by today components which is AEC-Q200, but is AEC-Q200 tested according to these tests criteria, it is not the automotive standard product, so cannot be used for automotive. Automotive standard products, yes, they are good for automotive. We can offer PPAP level, we can offer test report, everything, but not for industrial AEC-Q200 tested components. Many industrial customers already ask for AEC-Q200 just because they know about them. Maybe it was designed before for a company who was automotive designing, and they know the quality level is high, but it means not if the component have AEC-Q is automatically good for automotive. Please get in contact with our sales guy and discuss about this issue, because if you use a non-automotive approved component, we cannot support you with PPAP levels. Another question. Okay, I cannot see so good this. Maybe this one is better. Huh? I have to make it bigger. No. What is the difference between? Oh, okay. One customer asked, what is the difference between rated current and saturation current? Oh, thank you also for this question. Big difference. Rated current, it's belong and it is defined by us. It don't exist, no standard existing. Is defined by the maximum self-heating. So rated current, you apply a certain level of current. Current generate heat because of the DC resistance. And when the component reach to make a self-heating of 40 degrees Celsius, so 30 degrees Celsius above the ambient temperature for delta T of 40 Kelvin, we say this is the rated current maximum, which generate 40 Kelvin. Because if you use an ambient temperature of 85 degrees plus the self-heating, you reach the 125 degrees Celsius of the maximum operating temperature. This doesn't take care about the saturation point. Rated current doesn't care about inductance. He cares only just about temperature. Now, if you take the saturation current in comparison, the saturation current doesn't care about temperature. The saturation current look always to the inductance value. So by zero DC bias load, it may have an inductance like 100 microhenry, and then you start to apply DC current, and you increase the DC current, increase the inductance, is stay the same 100%, 100 microhenry, and at a certain point it start to drop. When the inductance drop from 100 microhenry to 90 microhenry, it means it drops 10% of his initial value. Then we say stop to use them, it's saturated. Is no standard worldwide to define when it is to be defined saturated. Würth Elektronik defined by the PDA example, when your inductance value drop 10%, we say stop them, don't use them, because it start to be very aggressive exponential dropping, and don't use them, more like 10% of this inductance drop. Some of those inductance, like who has a linear saturation, we even admit sometimes more like 10%. We admit maybe 30% saturation, because the saturation curve is very linear, especially like for iron powder cores. A linear saturation means it's not dropped so fast. So 30% drop, it's quite okay. So it's dropped from 100 micro to 70 micro, but it's not dropping so fast like we say like a knee saturation. It's very, very fast dropping. We stop them by 10%. But this is not taking care about temperature. You can see all that in the data sheet, or if you go to the Red Expert, of course, in Red Expert, you will see as well the saturation current and the temperature rise by temperature and current graph. And you can play with these cursors. And I tell you now another secret. In Red Expert, you can see measured value, it's not simulated value, measured value at different ambient temperature. In a data sheet, you have always laboratory conditions, 20 degrees Celsius. In Red Expert, you can go with a small selection button on the right side, and you can decide ambient minus 50 degree, minus 40 degree, plus 85 degree, plus 125 degree, and you can see what is shifting the saturation point or what is the influence of the ambient temperature to the core. This is in Red Expert measured, so you're welcome to try out. Other questions? Chat, again, chat, open the chat. It's always closing. Question. Why is a shielded inductor better as a rod core inductor? Like I told you, a rod core inductor, thank you for this question as well. Rod core inductor is a non-shielded inductor. It has a north and south pole. If you apply current to this rod core, it makes a magnetic field, which is open magnetic field. And if you want to have a good magnetic shielding, you need a rod core inductor with a shielding on top on it, because this shielding make that the magnetic field is turned back on the shortest way and don't make emission to the EMI receiver antenna. That's the reason of shielded is much better like a unshielded version. Second point of the advantage, when you have a shielding, you have more ferrite, you have more meat around the core, and then you can reach the same inductance value in the same package with less number of turns, and your dis resistance will be better because you don't use so much wire, or you can put a thicker wire and less number of turns. Automatically is advantage in terms of efficiency, automatic efficiency in terms of EMI. Okay, I don't see any other new question. It looks like everybody's happy. Nobody trusts to put questions.
All right. Okay, no, so Laurent, I don't see any other questions as well. Well, I'd like to say thank you for this webinar, and also I'd like to say thank you to all of our listeners. I hope next time we will hear each other again. And so yeah, I say goodbye and till next time.
Bye bye. Thank you.